Welcome to the online lecture series of turbo machines. Here is Professor Lakshman Mane. This is lecture on steam turbines, part 1, that is steam nozzles, velocity of steam and mass flow rate. I acknowledge my sincere thanks to the following author and courtesy for being used these concepts to make this video session. In this session, you will be able to illustrate types of steam nozzles. You will be able to explain equation of velocity in steam nozzle, and you will also be able to explain mass flow rate of steam. So, discuss about steam nozzles. Turbo machines like steam turbines produce power by utilizing kinetic energy of steam jet produced by passing high pressure steam through the devices called as nozzles. So here we see this is a steam turbine which is run by injecting steam through the device is called as steam nozzle. So it is a passage of varying cross-sectional area by means of which pressure energy of working fluid as a steam is converted into kinetic energy. Types of nozzles. There are mainly three types: convergent nozzle, divergent nozzle and convergent divergent nozzle. Let us see one by one. Convergent nozzle. In convergent nozzle, the cross-sectional area decreases continuously from inlet to outlet. This nozzle is used in case when pressure ratio, that is P2 by P1, is equal to or greater than the critical pressure ratio, and critical pressure ratio value is up to 0.58. Divergent nozzle. The cross-sectional area of divergent nozzle increases continuously from inlet to outlet, and it is used in a case when the pressure ratio is less than the critical pressure ratio. Convergent divergent nozzle. In this type, the cross-sectional area first decreases from inlet to throat and then increases from throat to outlet. So here we see this is a first part of nozzle where the area from inlet to throat is decreasing, and onwards throat to outlet it is increasing. So this first part is convergent region and the second part is divergent region. This type of nozzle is widely used in many type of steam turbines. Now we will see isentropic expansion of steam in a nozzle. So here we see this enthalpy entropy diagram. This is a saturation curve. This is an expansion process from 1 to 2, that is from pressure P1 to pressure P2. Point number 1 is in superheated zone and point number 2 is in wet region. Supersaturated flow in nozzles mean the flow of steam in the nozzle is in the state of supersaturated. How? That we will see. As steam expands in the nozzle, its pressure and temperature drop, and it is expected that the steam starts condensing when it strikes the saturation line. Means at this point, saturation line, steam should start condensing. or it is expected, but due to high velocities, the residence time of the steam in the nozzle is small and there may not sufficient time for the necessary heat transfer and the formation of liquid droplets. Hence, consequently, the condensation of steam is delayed for a little while. This phenomenon is known as supersaturation, and the steam that exists in the wet region at this point without containing any liquid is known as supersaturated steam. Now, here is a dashed line or curve. So this is the locus of points where condensation will take place regardless of the initial temperature and pressure at the nozzle inlet is called as Wilson line. So this is a Wilson line. Now where it is situated, Wilson line lies between 4 and 5% moisture curves. Moisture curve means dryness fraction lines inside the dome. So the Wilson lines lies between 4 and 5% moisture curves in the saturation region on the HS diagram for the steam and is often approximated by the 4% moisture line. 4% moisture line means this is about at dryness fraction value of 0.96. This is X, that is dryness fraction. Now we will see equation of velocity in nozzles. So consider steam passing through the nozzle from inlet 11 to outlet 22. So these are the various parameters. At inlet, say P1 is pressure, V1 velocity, T1 temperature, small v1 specific volume, H1 specific enthalpy, U1 internal energy and Z1 datum level of steam. Similarly, at the outlet of nozzle, the parameters are with suffix 2. So in nozzle, we say that steady flow energy equation. What is it? It is a total energy entering to the nozzle that is equal to total energy leaving from the nozzle. So total energy contains what? P1 V1, this is pressure energy, U1 internal energy, V1 square by 2G kinetic energy, GZ1 potential energy plus Q, that is heat energy. So these are the energies at inlet is equal to energies at outlet. Similarly, this W is what? Work. Now as P1 V1 plus U1 is equal to H1 means summation of pressure energy and internal energy, that is enthalpy. This is for inlet and this is for outlet. Hence above equation will be H1 plus V1 square by 2G plus CZ1 plus Q is equal to H2 plus V2 square by 2G plus ZZ2 plus W. Now as the nozzle is said horizontal, then change in potential energy is negligible, means Z1 is equal to Z2. And for adiabatic process, Q is equal to 0, means no heat transfer between system and surrounding. And for no work done, means nozzle do not do work done. So W is equal to 0. Hence by substituting this above equation will be H1 plus V1 square by 2G is equal to H2 plus V2 square by 2G. In the term of V2, we can have this equation. Now, as V1, that is velocity at inlet, is far less than velocity at outlet of nozzle, so V1 can be neglected or ignored. Thus, above equation will be V2 square is equal to twice of enthalpy difference between inlet and outlet. So velocity at outlet of nozzle will be equal to square root of 2 into H1 minus H2, provided here H is in kilojoule per kg and V2 is equal to square root of 2000 into H1 minus H2 in meter per second, where value of H is in joule per kg. Means here 1000 is a conversion from kilojoule to joule. So 2 into 1000, that is 2000. Now we will see about mass flow rate of steam through the nozzle. So we know that steam is a gas. So it is compressible fluid. Means density is changing, not constant. So steam flows through the turbine under steady state condition. Hence we take mass flow rate formula, that is rho into A into V is constant. Now if we arrange this equation as m dot is equal to A, area into velocity divided by specific volume, where specific volume is reciprocal of density. So here A is cross-sectional area of nozzle in meter square, V is velocity of steam in meter per second, and small v is specific volume of steam in kilogram per meter cube. Now we will use m dot is equal to area into velocity divided by specific volume as a constant, and we can have a relation taking log of both sides. So log of this both side. So here first of all this is a product and this is division. So for the product here will be log A plus log B, and here is a division, means minus log B is equal to constant log is 0. Now differentiating above equation, that is taking differentiation of log A, that is dA by A, differentiation of log B dV by V, and differentiation of V dV by V, and here is a minus sign as it is. Equation number 1. Now we will have here steady flow equation, Q minus W is equal to delta H plus delta PE plus delta KE. In differential form we can have this equation, say equation number 2. Now already we discussed, as the nozzle is horizontal, change in potential energy is 0, and in the nozzle no work. Thus enthalpy definition again, H is equal to U plus PV. This is internal energy and this is flow work, PV. In differential form, dH is equal to du plus derivative of flow work, PV, and this can be modified as PdV plus VdP. But summation of internal energy and this flow work, that is equal to dQ. Say equation number 3. So now the equation by using this will be here dH is equal to dQ plus VdP, that is 4, equation number 4. Now change in kinetic energy, that is V square by 2G change. So equation 2, that is in last slide, this equation 2, this will become dQ minus 0 is equal to dQ plus VdP. This is for dH, we place here, plus this is a work, that is 0, already we have discussed, plus d V square by 2. Now in this case on the both side dQ will get cancelled, and arranging the terms here we will find minus VdP is equal to d of V square by 2. Now derivative of V square, that is 2V. Now here 2 get cancelled, and then in the form of dV we can have this equation, that is equation number 5. Now from equation number 1 and 5 we can have dA by A minus VdP by V square plus dV by V is equal to 0. Further, this equation we will write in this way, taking VdP common from the bracket we find 1 by V square plus dV upon V square dP, bracket complete. Now why we do this? See, from fluid dynamics, velocity of sound, that is A, is given by, now here expression is given in the form of square. S square is equal to minus V square at dP divided by dV at constant entropy. Okay, now what happens? This we can replace this term with this second term. So that's why above equation is dA by A is equal to VdP bracket 1 by V square minus 1 upon A square. Now this V square we will take common outside of the bracket. dA by A is equal to VdP upon V square bracket 1 minus V square by A square bracket complete. Now the ratio of velocity V divided by A, that is nothing but Mach number. So dA by A is equal to VdP by V square bracket 1 minus M square. But already we have seen that minus VdP is equal to VdV. So substituting here, dA by A is equal to minus VdV by V square bracket 1 minus M square. So this is the equation. Now here we get cancelled, square. So we get dA by A is equal to minus dV by V bracket 1 minus M square. Now this is the equation which is used to decide type of nozzle. So on the basis of this equation, the nozzle, which kind of nozzle is used, that we see. Okay, we will see that now. Say, take for subsonic flow, means Mach number is less than 1. Okay, means velocity of steam is less than velocity of sound. So as we have dA by A is equal to minus dV by V bracket 1 minus M square bracket complete, this equation. Okay, now see, if Mach number is less than 1, means Mach number is negative. Okay, if Mach number is negative, this means this complete expression will be what? Positive, because minus minus plus. So this expression is positive. If this expression is positive, means left side will be negative, dA by A. Now as the ratio is negative, means dA is negative, and dA is what? Change in area, means what? Final area minus initial area. Now final area is a small area and initial area is large area. Small area minus large area, that is what? Negative area. Means this type of nozzle is what? From large area to small area conversion nozzle. Means for the subsonic flow, convergent nozzle is suitable. This is finalized with the help of this equation. Okay, similarly now we will proceed for the next case, where we will consider supersonic flow, means Mach number is greater than 1, that is velocity of steam is greater than velocity of sound. See, now this is the original expression. Okay, Mach number is greater than 1 means positive. Mach number is positive. So Mach number is positive means this expression dV by V bracket 1 minus M square, this expression should be negative. Okay, if this expression should be negative, means dA by A will be positive, this, and dA by A positive means dA is positive. Change in area is positive. Now change in area, large area minus small area is positive. Large area is next and small area is first. This kind of nozzle is which kind of nozzle? Divergent nozzle. It is cleared. Divergent nozzle is for supersonic flow. Now third case, that is sonic flow, where Mach number is 1, means velocity of steam and velocity of sound are same. Means what? This dV by V bracket 1 minus M square, that is equal to 0. Okay, 0 means dA by A, this left side term is 0, means dA is 0, means there is no change in area. No change in area means it is just like pi. But in actual case for sonic flow, the case is what? The nozzle is made up like this. First part is convergent throat and then next part is divergent. Why? See, fluid velocity is increased in conversion from subsonic flow to sonic flow. Means from subsonic flow, the flow is changing to sonic flow. Then in divergent region, flow from sonic to subsonic flow velocity, fluid velocity is increased from sonic flow to supersonic. Okay, so convergent divergent nozzle is used for the sonic flow. So at the end of this session, you can illustrate types of steam nozzles. You can explain equation of velocity in steam nozzle, and you can explain mass flow rate of steam. If you like this video, please subscribe and share. Thank you.